So good afternoon. My name is Itai Rosenberg, and I'm part of the StarCore engineering team. Welcome to part 3 of Stark One-on-One. I hope that you have, until now, a fruitful day, and that you even got some time to grab something to eat. In this talk, we are going to speak about the FRI commitment and the FRI protocol. But before we will do that, let's do a short recap. So we started the day by stating the main goal of today, which was to prove a statement on the Fibonacci square sequence. In order to do that, we constructed a trace in 1023 points. We then created the trace polynomial using Lagrange interpolation, and we then evaluate and committed on a larger domain. We then constructed 3 constraints on f of x. For example, this constraint. And then we created 3 rational functions from the constraints. For example, this rational function from the first constraint. We then created the composition polynomial, the CP, using random linear combination. And then the prover committed on the CP. Our goal is to show that CP is polynomial. This is our goal for this talk. We need to show that CP is polynomial, and if we will show that CP is polynomial, all the constraints will be satisfied. So we want to prove that CP is polynomial. However, we will not do that. We will instead prove that CP is close to a polynomial of low degree. I'm repeating on that because it's important. We will not prove that CP is polynomial. We will instead prove that CP is close to a polynomial of low degree. The reason why we are doing that is beyond the scope of this talk, but you can trust me that it is sufficient to prove that CP is close to a polynomial of low degree. So in order to continue, we need to understand what is low degree and what is close. So a low degree is some agreement between the prover and the verifier on some bounded degree that the polynomial is bounded by. And what is close? So in order to understand what is close, let us first understand the definition of distance. So the distance between a function f to a polynomial p is the number of points that f and p disagree on. For example, if we will take a look on the blue curve, which represents polynomial p, and the function f, which represented by the green dots, we can see that there are 5 different points that f and p disagree on. And therefore, the distance between f and p is exactly 5 in this example. So now we can understand what is close. So a function f is close to a polynomial p if the distance is small. And small is depending on the context. So our goal is, let us remember, our goal is to prove that CP is close to a polynomial of low degree. But how we are going to do that? So my first intuition was to do it by something that looks like this. It just convince the verifier and tell him, trust me, it's OK. But we are mathematicians, and they told me that I cannot do it, and we need to use some more mathematical method. So instead, we will use FRI and the FRI protocol. So before understanding what is the FRI protocol, let us understand what is FRI and what are these 3 letters stands for. So FRI, it's fast, read, Solomon Interactive Oracle Proof of Proximity. So this is the FRI. So why do we need it? So the goal of the FRI is to allow the prover convince the verifier that the commitment is close to a low degree polynomial. It allows the prover, in our case, to convince the verifier that CP is close to a low degree polynomial, which is exactly what we need. But how do we use it? So first, let us have a look on the protocol. At first, we receive random beta, which I will later explain. Then we apply the FRI operator, and we commit on it. We will do it repeatedly again and again and again until we reach to a point where we can just send to the verifier the result. So in a short time, I will explain how the FRI operator operates, but this is the protocol. What we are going to do now is to understand the protocol and how does it operate. So first, we will have some motivation regarding the FRI operator. Then we understand the FRI step. We'll have an overview of the FRI steps. And then we will take a closer look on the FRI operator and how does it operate. So first, motivation for the FRI operator, and we will not understand how does it operate. So our goal is to prove that a function is close to a polynomial of degree which is bounded by d. If we will apply the FRI operator once, we will get a new goal, which is to prove that a new function is close to a new polynomial, where the new function is half of the domain size, and the new polynomial is bounded by half of the degree bound of the previous one. So by applying the FRI operator once, we get a new goal, and the new polynomial is half of the degree bound. Still, we are not understand now how does it operate, but we understand the motivation. So if we will start with a function that we need to show that it's close to a polynomial of a degree bound of 1k, where the domain size is 8k, we can apply the FRI operator once, and we get a new function that we need to show that it's close to a polynomial of a bounded degree 512, where the domain size is 4k. So the problem after applying the FRI operator becomes smaller. So if we will take an overview for the FRI steps, we are starting with a function that calls the CP, and we need to show that it's close to a polynomial which is bounded by 1k. We can now receive a random beta and apply the FRI operator, and we get a new function which will be called CP1. And this CP1, we need to show that it's close to a polynomial which is bounded by only 512, where the domain size is 4k. We can now do it again and receive new random beta and apply the FRI operator and get a new function which will be called CP2. And now we need to show that CP2 is close to a polynomial of a bounded degree of 256, where the domain size is 2k. We can do it repeatedly again and again until we reach to the point where we need to show a new function which will be called CP10 is close to a polynomial of a bounded degree 1. In this point, we actually got a constant because the polynomial which is bounded by degree 1 is actually a constant. And at this point, we can stop. So the FRI steps looks like this cake. We start with a large layer, and in each step, the layer is reduced by half until we get to the point that it is constant. So now we will dive deeply into the FRI operator, and we will understand how does it operate. We only saw the motivation, and we still didn't understand how the verifier can be convinced that the prover didn't cheat him. In those steps, how the verifier can later understand that the prover actually computed all the transition correctly. And this will be covered in the next talk with me also. So now we will understand it. It will be a bit more mathematical, the FRI operator. But if you want to understand something, don't worry, because you're going to code it in a few minutes. So you will have plenty of opportunity to understand it. So in the left side, you're going to see the explanation. And on the right side, you will going to see the example. So we start with the function p0 of x, which is this function. And in the left side, you will see the explanation. So we're starting by splitting the function to even and odd powers. In this case, those are the even powers in the right side, and the odd powers is the bottom line. So we can we can call P0 of x, we can write it as gx squared plus x of hx squared. Each polynomial we can write as the sum of the even and odd powers in this way. And now this is the upper line is gx squared, and the lower line is x of hx squared. Now we receive the random beta. And the reason why we receive this random beta is in order to allow the verifier be convinced that the prover didn't cheat him. Because in each step, we get a new random beta from the verifier, and he can be convinced that the prover didn't compute it in advance. So the verifier sends the prover the random beta, and now the prover will compute a new function, P1 of y, which is gy plus beta h of y, where gy is this function in the right side, and h of y is the green function in the right side. So P1 of y in this case will be this function, which can be expressed as this function. So why did we need to do it? How does it help us? So this is the protocol as we have seen. Now we can understand that after we receive the random beta, we apply the FRI operator. In each step, after applying it, the degree bound is reduced by half. And we will stop. I told you that we're doing it repeatedly until we reach to some point. The point that we stop at is the point that we get a constant, where the degree of the polynomial is less than 1. At this point, we stop, and we just send to the verifier the constant number. So if we will take a closer look on a single step, we started with P0 of x, which is this function. And we received the random beta and applied the FRI operator. And then we got a new function, which is P1. And if we will take a closer look, we can see that we started with a degree bound of 6, because each power at the upper function is bounded by 6, is less than 6. And we finished with a degree bound of 3, because in the bottom line, the function P1, each power is less than 3. So in total, the degree of P1 is bounded by half of the degree of the previous function. And this is exactly what the FRI operator allows us to do. In each step, it reduces the degree bound by half, and by applying it a number of times, we reach to the point where we stay with a constant number, and then we just send him.